Hey folks, today we're going to be looking at graphing secant and cosecant functions. So to get us towards that, let's start by graphing this function right here. This is actually the second problem from your sine and cosine graphing worksheet. A few things I want to point out about it, and this problem will allow us to get into a few more deeper concepts as well. So we're going to do that. So what's the first thing you do? Well, the first thing I do is I determine what the length of one period is. What is the length of a full cycle? So to do that, we denote it with a t, and we take the normal length of a period for a sine and cosine graph, which is 2 pi, and we divide it by that coefficient in front of the x term. So I'm taking 2 pi, dividing it by pi to get 2. So I know it will take 2 units to go one full cycle. And now I want to do a couple other things. So now that we've determined the period, I want to go ahead and actually factor the inside of the function so that I can determine what my phase shift should be. So what I need to do is factor out, again, whatever the coefficient on the x term is. So I'm factoring out a pi from an x. I'm left with pi, just an x. And then I factor out a pi from a 3 pi, and I'm left with 3. Again, you can think of it as taking the term and dividing it by whatever you want to factor out. You're left with 3. And so we get this function, and we still have that negative 2 out in front. So I know I'm going to have an amplitude of 2, and I know that it is going to be flipped. So instead of going up to its first value, or I'm sorry, so instead of starting at its maximum value, this is a cosine function, instead of starting at its maximum value, it's going to start at its minimum value. So I will draw some axes, and I'm going to put a tick mark over here. I'm going to label it with the length of the period. We determined that the period had a length of 2, so I'm going to label that 2. And now I'm going to break this up into 4 equal pieces. I'm going to split it in half, call that 1, split it in half to get 1.5, and then I'll get 3 halves right in the middle. So the only thing we haven't yet talking about is the phase shift, which is going to be 3 units to the left, because we have that plus 3 right there. So I'm actually going to extend these axes out a little bit, give myself room to keep that same scale and go all the way to negative 3 like that, and then get negative 2 and negative 1, and then halfway in between each of those. So now I have the same scale on the left, same scale on the right. All I need to do is sketch this in. So my normal x value would be at 0, but we are shifting this graph to the left, so I know that I'm going to be starting at negative 3. Now we said that the amplitude was 2, so I'm going to mark 2 and negative 2. And then what I said a moment ago was, if you think about the cosine values on the unit circle, cosine is x. The x value of that first point is 1, but we're multiplying it by negative 2. So instead of starting at positive 1, I will be starting at negative 2. And so I get my first point right there. Well, after cosine starts, it then goes to 0, because again, cosine is x value. That is an x value of 0 right there. So cosine comes up to its 0. Cosine then hits negative 1, but again, we're multiplying that by negative 2, so we get positive 2. And now I'm going to just continue to oscillate between these points, moving between them each time I go 1 tick mark over. That's why it's nice setting up a scale that makes sense like this. We can plot all those points, and then we can try and sketch in a curve. And I'm very bad at it on this thing, but it's going to look something like that. Now, you may have noticed that we actually have a full period shift over before we actually even get back to the x value of 0. So that's happening because our period is 2, but our phase shift is 3. So we shifted over a length greater than our period. That means we have a period and a half there. So what I want you to notice is that we can actually think of a few different functions we could write this as. If you look at this bit right here, Notice that is the same exact thing. It's going to have the same period as this function here. It's starting at -2, just like that blue one, but it has only been shifted over by 1. What that means is I can rewrite this as y equals -2 cosine of pi times x plus 1 instead. And it's the same function because if you look at that pink thing, it can continue on forever and ever and ever. But notice how I got from 3 to 1. I subtracted 1 length of my period. It doesn't matter if you shift something to the left by a period or to the right by a full period, because moving it 1 full period does not affect what your graph actually looks like, because these are periodic functions. They will just repeat. So you can, I said so a lot, I'm noticing that. So you can always subtract or add periods in there to get that phase shift down to be smaller than a full period. Okay, that's cool. But what else can we notice? Well, let's go to a different function. And now I want you to focus on this part of the graph right there. That is also 1 full period of the graph. But notice that green thing is starting at the x value of 0. So I could write this as y equals, notice the amplitude is now +2 cosine of pi x, because the period is the same length, so I still need that pi in front of the x term, but it's starting at a positive value like cosine normally does. So I could write this as a positive version of the function as well. And notice there is no phase shift. And I'm going to do one last graph here. Notice the blue one now going there. Notice this blue one's first value is 0, then it goes to 2, then 0, then -2, then back to 0. Well, that's what a sine graph does. So this is like y equals 2 sine of, still has to be pi x because it is the same period, but this time it has a phase shift of plus 1/2 because it's shifted 1/2 to the left. And notice that is inside that factored form inside the function because I still need to take into account that modified period. My point is, all of these functions, all these equations that we just wrote, some of them positive, some of them negative, some with big phase shifts, some with small phase shifts, some with no phase shifts, they're all representing the same exact function. These functions, because of the identities, the cofunction identities, the parity of the function, even or odd, and the fact that they're periodic functions, all of that combined means there are infinitely many different ways that you could write every single trig function. So when we graph these, we want to take maybe complicated equations and we want to write them in the simplest way we can before we graph them. And to do that, I'm always going to start by factoring the inside. So if I factor the inside here, we'll get our cosine function. I'm going to factor out that -pi/3, and I'll be left with x minus something, but let's figure out what that something is. Remember what I said a moment ago, factoring out is like dividing the thing you're factoring by what you're factoring out. So pi divided by -pi/3, well, dividing by a fraction is the same as multiplying by that fraction's reciprocal, so -3/pi. Then notice my pi's cancel, and I'm left with -3. So that means I need a -3 inside right there, and I still have my -3/2 just like that. Okay, well, let's figure out what our period is. Period is going to be the normal 2 pi for a sine and cosine function divided by the coefficient, which again, -pi/3. Actually, I'm going to pause real quick because I want to think about one more thing. We know that cosine is an even function. If you think about what the graph looks like, that's how we normally draw it. But continue it back this way. It has perfect symmetry there across the y-axis. That means it is even. And if you recall, when we have a function that is even, like say x squared, if you have negative x quantity squared, that is exactly the same as x squared. So that means that when I'm writing this, I can say y equals -3/2 cosine of +pi/3. times x minus 3. So when I'm thinking about this period over here, I don't actually even care about that negative. It does not matter. Cosine is even, so once you factor out that negative, you can just get rid of it, make it positive. So let's figure out what this is. 2 pi times 3 over pi. Now my pi's cancel again, and I'm left with 2 times 3, which is 6. So period of 6, phase shift 3 to the right. Let's sketch this function. So I'm going to put the length of my period out here, which is 6, cut it in half, 3, cut it in half, 3 halves, cut it in half. If I count 3 halves, 6 halves, 9 halves, right there. And now let's graph it. So it's a cosine function. First off, let's get our amplitude in there. 3 halves and negative 3 halves. And now let's sketch this thing in. It is shifted to the right by 3 because of that minus 3 once we factored it. And we know that cosine, again, normally starts at positive 1. But we're multiplying it by negative 3 halves, so cosine will start down here at its minimum value instead. And then it goes to 0, and then it goes to its maximum. And I'm going to continue this pattern backwards in the opposite direction, like that, and now I can draw it in. And I'm done. That's all I need to do, just one single period, and there we have it. So now let's see how we can take these sine and cosine graphs and graph cosecant and secant graphs, or graph the functions, I should say. And to do that, we're going to think back all the way to Unit 2. So Unit 2 is polynomials and rational functions. Let's graph this function right here. Let's think about what we know. We know that this function has zeros at negative 2, right there. Sorry. Let's do a different. Negative 2, right there. Also at positive 1, right there. And finally at positive 3 as well. And how do I know that? Well, it's in factored form. Negative 2 plus 2 is 0. 1 minus 1 is 0. And 3 minus 3 is 0. So we're trying to make those factors 0. Well, now think about the degree of this function, meaning what's the highest power it would have if we multiplied all these factors together. Well, there are 3 x's there that would be multiplied together, so this is a cubic function, which looks like that. It's a positive cubic function, which means it will start down to the left and end up to the right. And then I can sketch it in just like that. But then the question is, what if I want to graph the reciprocal of this function? Well, what do I do then? Well, think about what the reciprocal is. It's 1 divided by whatever you want to take the reciprocal of. So we had all of these zeros from the numerator of that function, but now all those zeros are in the denominator. Well, remember what happens when a zero is in the denominator. You can't divide by 0, and because of that, you end up with vertical asymptotes wherever we have those zeros. So I can sketch these in pretty quickly. And remember what your graph does as it approaches a vertical asymptote. It can't cross it, but it has to get infinitely close to it. And you end up with your function going either to positive infinity or negative infinity. And which infinity it goes to totally depends on the sign of your function. And when I say sign, I mean S-I-G-N. So if you look at this section to the left here, I know I'm negative for my rational function because the blue function is negative. In between my 2 zeros, my 2 vertical asymptotes there, that blue function is totally positive. So my purple function is totally positive. And the other side there, between these next 2 asymptotes, my blue function is totally negative. So my purple function is totally negative as well. And then finally in the end here, my blue function is positive, and so my rational function, the purple function, the reciprocal of the blue function, is also positive. And that's it, and it's very painless to sketch that if you know the shape of the original function. Well, think about how that applies here. We know the shape of sine and cosine functions, so it's going to be just as easy to graph their reciprocals, cosecant and secant. So let's just think about the basic shape of this graph. If I graph y equals sine x, split this up into 4 pieces like I always do, and then I can plot this graph pretty quickly. And it's going to curve in and look mostly like that. And again, we have 2 pi over there. All right, well, think about what we said. Anywhere we have zeros, we will get vertical asymptotes. So I'm going to have 3 vertical asymptotes right there. And our function will approach either positive or negative infinity as the sine function approaches those asymptotes, and it depends on whether or not it is positive or negative. One last thing we need to think of is that these maximum values right here are positive 1 and negative 1. The reciprocal of 1 is 1, and the reciprocal of negative 1 is negative 1. That means these points will be on both graphs. And then all I need to do is sketch that in just like that. So if we know where the zeros are and we know where the maximum and minimum values are, then we can sketch the reciprocal cosecant very, very painlessly. So let's go ahead and graph this function now. Cosecant is the reciprocal of sine. So let's graph this as if it were a sine graph, and then all we have to do is flip it. So let's think about what we need to do. We need to figure out the period, which is going to be 2 pi divided by, oh, I forgot to write an x. There should be an x right there. My bad. So 2 pi divided by the coefficient on x, which is negative pi over 2. But we're going to be able to get rid of that negative in a moment, so I'm going to leave it as a pi over 2, just like that. So 2 pi times the reciprocal of pi over 2 is 2 over pi. My pi's cancel, and I'm left with 4. Okay, let's factor the inside here, and we will get, and let's think of this as a sine graph, we're factoring that negative pi over 2 out. Negative pi over 2 times quantity x plus something. Let's figure out what that something is. Take that phase shift of 4 pi and divide out the coefficient, which negative 4 pi, we're dividing out a negative pi over 2. Let's change this into multiplication. Make it negative 4 pi times the reciprocal there, so 2 over pi, and it's negative. Well, what do we get? The pi's cancel, and we're left with a positive 8. So x plus 8 on the inside there, and I still have my negative 2 out front. But what is the parity of the sine graph? Well, sine is an odd function. If you have an odd function like negative x cubed, let's say, well, that's the same as negative x quantity cubed, which means we can take that negative and we can pull it out front. So I'm going to pull that negative out front, so we have a negative times a negative, which gives us just a positive. So this is the same as 2 sine of pi over 2 x plus 8. Okay, it's looking simpler, but it's not fully there yet. We can go a little bit farther because we know the period is 4 and the phase shift is 8. The phase shift is just 2 periods, which means if you think about the unit circle, if I normally am starting right here, well, I'm going 1 full period around, another full period around, I'm back where I started. So adding or subtracting multiples of a period, it does not change your graph. And so it doesn't do anything, which means this function is actually y equals 2 sine of pi over 2 times x. It sounded like I was saying something else, but pi over 2 x. Because the phase shift does not affect it because it is an entire period. So let's graph this right here. I know that I'm going to have an amplitude of 2, so I'll put 2 and negative 2 there. And I know that my period, we said, was 4. So I'm going to put a 4 over here, and I'm going to break it down just like I always do. Now, what do we know? Sine starts at its minimum, and then goes to its maximum, then back to 0, then to its minimum, and then back to 0. I said it starts at its minimum. I meant to say 0. Now, at this point, I could go ahead and sketch that in, and then do everything I did on the previous page. But I don't actually need to. What do we know? We know that zeros become vertical asymptotes, and we also know that the minimum and maximum values are shared by sine and cosecant. So all I need to do is start at that maximum and go up, and start at that minimum and go down. And I am done. That's it. Okay, well that was sine and cosecant. What about cosine and secant? Well, think about the difference between sine and cosine. They're exactly the same, except they are shifted by 90 degrees. It's as if this was a sine graph. Picture that going down there. It's the same as a sine graph that's been shifted to the right by pi over 2. So that means all we need to do is the same exact thing before. Any spot we have a 0 will become a vertical asymptote. At any spot we have a maximum or a minimum value will become the opposite on the other graph. So see, this minimum here became a relative maximum right there. This maximum becomes a relative minimum. And it looks weird, but I could continue it out like that on both sides there. We know that's what it's going to look like. But that is all we need right there. Notice that this is an even function. It has perfect symmetry across the y-axis right there. Cosine is even, and so is secant. And back here, sine is odd, and so is cosecant. It stays the same. So let's graph one more of these, and then we will call it a day. So what do? We factor it. So we're going to factor out the 3. We're left with x minus, let's figure out what we're left with. We need to take pi over 8, and we need to divide that by 3, which is the same as just saying pi over 8 times 3, which is pi over 24, which is kind of awkward, but it will be okay. We have a pi over 24 right there, 1/2, and secant is the reciprocal of cosine. So we're going to think of this in terms of cosine and see where it gets us. Let's figure out what our period is. The period t is going to be the normal period of 2 pi, but we're going to divide that by that coefficient of 3. And so 1 full period is 2 pi over 3, which is a little awkward. But let's go ahead and see what we can do. Graphing in the same way I always do, I'm going to put a tick mark here for 2 pi over 3, and I'm going to split this into quarters. Now, I need to figure out what the value of one of those quarters is, so I need to take 2 pi over 3, and I need to divide it by 4, which again is the same as 2 pi over 3 times 4, which is 2 pi over 12, or if you like it, pi over 6. So I've got pi over 6 right there. I've got 2 pi over 6, which is pi over 3, and then I've got 3 pi over 6, which is pi over 2. So these are kind of interesting units we have here. But notice again, I have a phase shift of pi over 24. And so if each of these tick marks is pi over 6, well, how many pi over 24s goes into pi over 6? Well, that's like saying, what is pi over 6 divided by pi over 24, which is the same as 24 over pi being multiplied. And your pi's cancel, and you're left with 24 divided by 6, which is 4. So I need to split each of these little increments up into 4 more pieces. So although this is a little bit obnoxious, it's certainly not super hard to do. We just need to think about the fractions. And now I make it look like kind of a ruler. I've got my big tick marks for my pi over 6's, and then I got these little tick marks to indicate the pi over 24's. And that should do it, and let's see what our transformation is. It's to the right by pi over 24, so every point I would put in there, I'm actually going to start pi over 4 to the right. So, first point for cosine is its maximum value, so I'm going to put my maximum value in right there. Then it's going to go to 0, so I'm right there. And then it's going to go to its minimum value, so I'm right there. And then it's going to go back to 0, so I'm there. And finally, it's going to end again at its maximum value, so I'll finish right up there. Can you picture that cosine graph coming in and going up like that? Yep, I can. But what do we know? We know that zeros become vertical asymptotes. And we also know that the maximum values turn into relative minimums, and we know that the minimum values turn into relative maximums, and we can sketch it all in just like that, and we're done. Notice it's a little awkward with those units we've used, but make sure that you shift every single point. So every single of those points we plotted is one small tick mark to the right of a big tick mark. So let's summarize real quick. We have a cosecant function right here. I'm sorry, we have a, what is that? It says it's a sine graph right there, and we want to know how to graph a cosecant function with the same transformations. Well, think about what happens. We said zeros become vertical asymptotes. So everywhere I have a 0, I'm going to turn that into a vertical asymptote. And there we go. And what else do we know? Well, we know that all of the minimum values and maximum values are shared between both graphs. So all I have to do is sketch my function coming off of them, going towards those vertical asymptotes, and that's it. Although I'm not a very good artist and this is super sloppy, that is absolutely what it should look like. And we're done.